Good afternoon, everyone. Welcome back to the online faculty development program on artificial intelligence, machine learning, and data science with research application. It is my great privilege to read today's resource person, VENINGSTON sir. My hearty welcome to this online FTP, sir. Welcome. VENINGSTON K received a PhD in computer science and engineering from Anna University, Chennai in 2015 and is currently working as an assistant professor in the Department of Computer Science and Engineering at the National Institute of Technology, Srinagar. He has over 12 years of teaching, research, and consultancy experience and is currently guiding 5 full-time PhD scholars working on various facets of artificial intelligence. His expertise includes designing and implementing computer vision and natural language processing systems using machine learning and deep learning algorithms. His work includes generative AI and CV applications in healthcare, NLP applications in judicial and legal domain, and machine learning optimization techniques.
Dr. Ajmira,
He received
can you hear me?
prestigious Innovation in Science Pursuit for Inspired Research Fellowship from the Department of Science and Technology, Government of India in 2011 with financial aid of rupees 10 lakhs. He was a recipient of the Senior Research Fellow Professional of the Department of Science and Technology, Government of India. He has chaired technical sessions at several international conferences within and outside India and delivered numerous invited talks and keynote lectures on the allied areas of his research. He has published over 20 research papers in reputed journals and conferences, besides undertaking a research project worth rupees 11 lakh sponsored by Jammu and Kashmir Science and
I'm not able to
Technology
hear.
Innovation Council.
Dr. Ajmira, I'm not able to hear. Can you hear me?
Yeah, yeah, audible, sir.
Right, but on the meeting link,
Hey, start the mic.
is my voice audible?
You can unmute yourself. Sir.
Okay, I unmuted and but I'm not able to.
Answer.
He has published over 20 research papers in reputed journals and conferences, besides undertaking a research project worth rupees 11 lakhs sponsored by the Jammu and Kashmir Science and Technology and Innovation Council, being contributed to the Swachh Bharat mission of the Government of India. He has an Indian patent published on intelligent transportation system for emergency vehicles to his credit. He qualified for the University Grants Commission National Eligibility Certificate UGC NET in 2012. So it's a great profile to have our resource person with us today. So have a happy learn.
Sir, try it now, sir. Can you speak, sir? Venningston, sir. Venningston, sir. Are you there? Venningston, sir. Sir, are you there, sir?
Yeah, I'm here.
Now it's is it fine, sir?
Yes. I can hear you now. Yes. Can you hear me? Am I
Yes,
audible?
yes, sir. Now fine, sir.
Okay. If it is fine, yeah, we can start.
Yes, sir. Saptam, please
For the session.
take over the session.
Welcome, sir. Welcome to the online faculty development program on artificial intelligence, machine learning, and data science with research applications. It's my great privilege to read your profile, sir. Uh, Wenningston K received a PhD in computer science and engineering from Anna University, Chennai in 2015 and is currently working as an assistant professor in Department of Computer Science and Engineering at the National Institute of Technology, Srinagar. He has over 12 years of teaching, research, and consultancy experience and is currently guiding 5 full-time PhD scholars working on various facets of artificial intelligence. His expertise includes designing and implementing computer vision and natural language processing systems using machine learning and deep learning algorithms. His works include generative AI and CV applications in healthcare, NLP applications in the judicial and legal domain, and machine learning optimization techniques. He received a prestigious Innovation in Science Pursuit for Inspired Research Fellowship from the Department of Science and Technology, Government of India in 2011 with financial aid of rupees 10 lakhs. He was a recipient of the Senior Research Fellow Professional of the Department of Science and Technology, Government of India. He has chaired technical sessions at several international conferences within and outside India and delivered numerous invited talks and keynote lectures on the allied areas of his research. He has published over 20 research papers in reputed journals and conferences. Besides this, he is a member of the Multitask, sponsored by the Jammu and Kashmir Science and Technology and Innovation Council, being contributed to the Swachh Bharat mission of the Government of India. He has an Indian patent published on intelligent transportation system for emergency vehicles to his credit. He qualified for the University Grants Commissioner National Eligibility Certificate UGC NET in 2012. It's a great profile, sir. We are honored to have you here. Now I request Wenningston sir to take over this session.
Thank you, Dr. Ashmira and your team. Sorry, I made you read the profile, I think, yet again. I hope my
It's okay,
screen
sir.
is
No
visible.
problem.
I
Yeah,
hope my
yeah.
screen is visible. Fine.
Yes, sir. Visible, sir.
Visible.
Okay, right.
Can I have a photograph, sir? Can you please switch on the camera? I have a photo.
Yeah. Should I stay on video throughout the lecture?
No, sir, you can we can turn off the video, sir.
Okay, right. Is it done?
Turn your camera, sir. We'll take a photo of this session.
Okay, fine. Okay, let's get started. So basically, we are going to discuss about three different aspects of learning when it comes to image recognition task. Okay. So we predominantly see image classification, image recognition task wide across different domains. So we see image recognition tasks in security applications. We see image recognition tasks in healthcare, and then we even see image recognition tasks in agriculture as well, agriculture field as well. where we take a picture of a particular plant and then we classify whether the plant is healthy or not. Then we take a radiology image from medical domain and then we see if there is a presence of any abnormality or not. In case there is an abnormality, what kind of abnormality it is. Okay. These are the various kinds of image recognition tasks we widely see across the domain. So considering its importance, there are basically different frameworks that helps us in the early days without even before the deep learning gets very much popularized, and especially in case of image recognition applications. We had a traditional way of doing it, and we were able to relatively do it well, even with a very limited amount of data. Okay. So when the data became available and a huge amount of data is available on different domains, and then we started adopting to deep learning frameworks, and then keeping a model very complex, and then keeping a very large collection of data, and then we were able to model lot of we were able to build models for image recognition tasks. Okay. Yes, the talk is going to be around deep learning, especially with a focus on convolutional neural networks. I believe that somewhere or the other way, all of us are a bit comfortable with convolutional neural network because of its popularity, and we do see a lot of applications on convolutional neural network, especially when it comes to computer vision related tasks. Okay. So first, let's start with understanding what is transfer learning, and then we'll move on to something called multitask learning. Multitask learning is something that is not new. The very first paper on multitask learning was published in 1997. It was introduced way back, about 3 decades ago. But it also makes sense in the current scenario. So we'll take a couple of use cases and then understand what is this multitask learning is all about. And then finally, we'll move towards something called end-to-end learning or end-to-end deep learning. So as this end-to-end learning actually focused on convolutional neural networks, so nothing wrong in calling it simply an end-to-end learning or end-to-end deep learning. Right? Right. So first, let us understand what is transfer learning. Mm. For example, basically, if you consider the task which I wanted to solve, um, is something like this. So let's consider an image. Let's consider an image, a sort of X-ray image, or any image from medical imaging, any image from medical imaging. It can be an X-ray image or CT scan image or MRI image or any other USG sort of images. Right. So we have an X-ray image and we wanted to basically um, find out whether there is an abnormality, is abnormal or normal. Let's consider a simple two-class classification task here. So in case if the image has an abnormality, then we are going to label it with abnormal. So in case if there is an image which has no abnormality, then we are going to assign label normal. Okay. So basically, we wanted to train a machine learning model or train a classifier, so which is going to take an image and then it is going to assign one of these two labels. Well, that is the task, and that is the model that we wanted to build. So in order to build such a model, so we require probably thousands of images which are abnormal and thousands of images which are normal, and then we can give these two set of two no, group of large set of images into the model, and then let the model understand the inherent properties from each of these two categories of images. Okay? So model will try to identify some sort of discriminative features to classify a given image into one of these two categories. Okay, obviously, model cannot take a middle. Model cannot actually take two stand. For example, model cannot actually assign both abnormal label as well as normal label to an image, and model is expected to actually assign one of these two labels. Okay, basically output a probability value to both of these outcome, that is either abnormal or normal, and based on the amount of based on the density with which a particular class gets the probability marks, and appropriately the image will be labeled either normal or abnormal. So this is the task that we consider for understanding the classification task or classification problem. Okay. And in order to train such a model, we can basically go for a standard convolutional neural network. And there are several architectures which are based on CNN. There is something called LaneNet. There is something called VGGNet. We have VGG16 and then VGG19, and then we have something called GoogleNet, and then we have something called AlexNet, and then we have ResNet, and then many more. We have nowadays we see a lot of lightweight convolutional neural network. We have nowadays we see a lot of lightweight convolutional neural network models such as MobileNet. So mostly all of these models were initially trained on a very large collection of images from ImageNet. So ImageNet is a image recognition challenge. This dataset contains thousands of categories of images, and for each category there are thousands of images. And this dataset is built, and these standard CNN models were basically trained on this particular dataset in order to understand or in order to assign label for image. And the number of labels in this case is not just two or three, it's going to be in thousands. Okay. So basically, this data set is a very large data set, and in which there are 1,000 categories. I think there are 1,000 different categories of images which are part of this data set, and these models were trained and tested on this challenge. And then we see that these models, especially when it comes to ResNet was able to perform very well, even beyond the human level accuracy, okay, of making around no mistakes of probably 2 to 3 images per 100 images. So given 100 images, the model makes mistake only in classifying 2 or 3 images. Okay, so even if you give it to any standard human user, probably they would probably work at the accuracy of probably 93 or 94%. So now these models are very much popular just because of this ImageNet challenge, because these models were able to perform very well on ImageNet dataset, especially in recognizing images of different types or different categories. So with this inclusion, actually, we later then try to adopt this CNN architecture into various fields, especially in case of medical. We find a lot of applications. We have this, given an X-ray image, and we can find out whether there is whether the person is infected with COVID or not, or in case the person is infected, and or in case a person is infected, let's say with a tumor. Uh, an X-ray image has the presence of tumor cells, and interested in building a model which can help us locate where exactly the tumor is present, which part of the X-ray has this tumor cell present, so that the appropriate medical diagnosis can be made from the medical imaging. So these are various applications that we see, especially in healthcare, and yes, we can also see many other relevant applications in other fields as well. Okay. So now in this task, yes, there is already a pre-trained CNN models, so which are very well aware in order to extract meaningful features from the image and then make a classification decision. right? So especially the images which are part of this image net are not from medical domain. So they are basically from they are most of the images which are part of image net are natural images. Probably there may be a collection of sheep images, there may be a collection of different animal images, there may be a collection of seashore images, and then hills images, and then whatnot. Okay, you can think of many categories, and basically this image net is made up of images from natural space, a kind of natural sceneries that are captured, and then this data set was built. But still, these models were trained to extract meaningful features from this, and then to classify one out of assign a label out of thousand possible categories. Okay, so now the what we basically wanted to do here is, so in order to train, let's say, a model, so which can predict the medical, which can help us in making medical diagnosis by training a model. Okay, so in order to probably train a model right from scratch, especially we wanted to, let's say, train this AlexNet for making this medical diagnosis or helping us in medical diagnosis. Okay. So what we can do, the first option that we have with us is to retrain completely this network, AlexNet, with the help of set of training instances. As I mentioned before, probably now we can freshly from scratch we can try to train this AlexNet model now on this particular data set. Okay, so this is what we generally do in order to build a medical diagnosis which can help us know upon taking an image, and then it will assign one of these two labels. Okay, so it depends on the medical diagnosis that you wanted to carry out, and you must have appropriate training data set with you so that you can train a respective model, and then you can test it. You can test it, and then if it is performing well, then you can take it for actual deployment so that it can help medical practitioner in diagnosing medical of these type of medical images. Solution that we have, but if you look at basically this BGG net, Google Net, AlexNet, ResNet. So these models are relatively very big. So very complex models, and the model has several millions of parameters. If you take page 16, and it has probably 16 layers, 90 layers, and actually this number actually denotes that the number of layers which are part of this network. And again, when it comes to ResNet, it comes in various formats. That you have some ResNet architecture in which you have 50 layers, 52 layers, and then there is a variant of ResNet in which you have 100 plus layers and so on. Okay. Yes, and then besides simply increasing the number of layers, so it also in convolutional neural network as sometimes results in many other especially when it comes to learning parameters of this model. So they have introduced something called residual blocks and so on, so as to minimize the number of parameters, or so as to learn the parameters value so that the model converges reasonably in less number of training cycles. Right. So this is one standard solution we have. We can take one of the popular models from this class of CNN architectures we have, and then given a large scale data set available with us, given large scale data set available with us from a particular domain. So we can afresh we can train these models completely so that we can finalize the model for deployment. So this is one solution. So people generally don't want to do this because as this model has several parameters, so you can basically think of all these models as basically a function. Mathematically, you can represent each of these models as a function that learns the mapping from x to y. So where x is your input image, while y is the label that will be assigned. So whether zero label or one label or true label or false label or abnormal or normal. Okay, so that is how in a two-class classification setup you can think of each of these models as as if it has the capability to map x to y. So given x, so given an instance of an image, and this model will be able to give you a label which is appropriate to the given input image. Okay, so now the model actually here acts as this function. This function f is what the actual model. Function f is what the actual model. And now, when it is a function in standard programming practices as well as a function in mathematics sense, a function will have certain parameters. Okay, so function will operate on certain parameters theta over x. And what are these? What are these theta? So theta is basically a set of parameters which are aligned with this particular function. Okay, so from the CNN point of view, from a neural network point of view, the theta defines the number of weights that are part of a network. Okay, so CNN is neural network itself. So obviously there will be set of neurons in it, and then the neurons from one layer will get connected with other neurons in the other layer, and subsequent layers and so on, all the way up to the final layer that is responsible for projecting the output. Okay. So now, whenever there is a connection between a neuron and another neuron in the next layer, there will be a weight associated to that link. Okay, so that weight set of weights and biases in the context of neural network is what parameters in the context of function that helps us obtain the mapping from x to y. So now, when it comes to this data set and all the X-ray images defines X part, and then this Y part contains this label either abnormal or normal. Okay, so you must have a large data set in which you have close to each other. Number of samples of normal should be similar to the number of abnormal samples, so that your model will not end up learning more from the dominant images. For example, in case if this in case if these two categories of images are not properly balanced, then there is bias, right? So the bias will always corresponds to the dominant class. Let's say instead of 10,000 images of normal, you have, let's say, 7,000 images of normal category, and you have, let's say, 13,000 images of abnormal category. So since abnormal category is dominant in your data set, and your model will learn more from the abnormal category over normal category. Okay, so obviously model will be slightly biased towards abnormal category compared to a normal category. And that is the reason why it is a standard practice to keep the balance across the categories, across the category. In this case, we are solving two plus classification problems, so we can just keep the number of images from training instances for each of those categories, which are slightly matches with each other in terms of number of instances we have in the dataset. Okay, so now we would use this large collection of dataset for freshly training a model. Okay? So this is one practice. But on the other, as each of these models comes with a set of parameters, and these parameters are going to be very, very large in size, which are going to be in millions. So even considering this PGG, GoogleNet, AlexNet, ResNet, and then other variants of convolutional neural networks, the number of parameters are in generally millions. So there are millions and millions of parameters which are associated with this model. But while training a model, while training these models on a particular domain, and you will have to actually learn those many parameters, and you cannot basically learn all these parameters in one go. Basically, if your model is expected to actually scan your entire training set for several steps, and on several, that is what actually basically your parameters will be updated over epochs. In every epoch, the model parameters will be updated, and then the model will be evaluated against certain objectives. And if your model is not performing well, then we will go back, and then we would, if the model is making errors, then we would propagate the error towards the backward of the network, and then we would fine tune the parameters. We will fine tune the weight values, and then we would once again evaluate the model. And the model is expected to actually minimize the loss over epoch. Right? There are clever optimization algorithms are available. And we have wide range of choices for optimization algorithms. Primarily we use something called Adam Optimizer, RMS Prop, Adaptive. These are some of the popular optimization algorithms we have, and which are proven to be successful in some sense. And then you will have to actually, and this process will continue, over several epochs, and then probably you will have to run several hundreds of epochs before converging the model with the right set of parameters that makes less error while mapping from X to Y. So that is the model, that is the ideal model that we are interested in, so that we can evaluate it and then appropriate we can take it for deployment. Okay? So basically, this entire process requires takes a lot of time. Especially when you try to tune this model, especially for a particular domain. Okay, but on the other hand, what researchers have tried to do is by using transfer learning, so that what people have done, you can choose any model from this class of CNN architectures. Probably you can take, let's say, BGG16. You can take this model. You can take this model, and this is a CNN architecture. So basically, to recollect the architecture of CNN, so which basically contains two components. So one is it will have a set of conditional layers. For example, there is input X. X will be probably, if in case if X is an image of size 30 cross 30, then every image R would be represented in terms of a vector containing 900 real values. Okay, so this X is basically, every X is going to be a vector containing it is 900. It's 900 real values. It depends on the size of image that you process. If you consider size of the image being 30 cross 30, then every image will be represented with a set of 900 pixels, and we need to represent each of those images in terms of a vector containing 900 real values. Okay, and now we're going to have, let's say, sequence of something called a convolutional layer. So we have convolutional layer. So the use of this convolutional layer is to actually help us in performing feature engineering. So basically, the prime responsibility of convolutional layer is to apply various filters over images. Basically, we don't go by any handcrafted features. We don't go by any standard filters like edge filter or sort of image enhancement filter or blur filter or sort of a kind of standard filters that are primarily used in image processing domain, right? We don't actually basically do it while training a CNN, okay? Because CNN has the flexibility to learn its own set of features. So we just use random curve size or the filter size, and then we would deploy filters of varying sizes and then filters of various numbers, so that we will be able to learn very good number of low level features from each of these images. Okay, so especially when we try to learn filters of our own on any CNN architecture. So we may not be able to explain each of those features. Okay, for example, in standard filters that we see in image processing domain, like blur filter or edge detection filter, or sort of image enhancement filter, which improves the quality of the picture. So all these filters are actually tested well on different applications, and we can know, especially when we use filters in the context of CNN. So we may not be able to explain all the filters, but still we have the flexibility, we have the liberty to have as many filters as per our choice, so that you can learn huge number of low level features from the input that you are using in order to train your model. So that is what all that convolution layer is actually basically doing. So this helps us in extracting meaningful features from the image. And once the required features are extracted from the training set, then next we are going to have, then we would finally flatten this. Finally, we would flatten the representation, the image feature map that you get out of applying various convolutional filters on this intermediate image, input image, as well as the intermediate representation of image. And then finally you will get a probably a minimized image representation, so which will be very much different from the actual input, but this image that you obtain all size of image, let's say it is only 10 cross 10. Okay, so you have basically condensed your image from image of size 32, 30 cross 32, a low level representation of 10 cross 10, so that this representation will now be represented in terms of a vector containing only 100 values. And now you would flatten this 100 vector containing 100 real values, and then you will flatten, and then you will connect something called fully connected layer. Okay, fully connected layer is your standard neural network in which you can have multiple layers, and every neuron in one layer will be connected with the neurons in the next layer. Neurons in the second layer will get connected with all the neurons in the subsequent layer, and so on. Okay, so you can also have this fully connected layer with any depth. You can also decide to have the number of the fully connected layers that you wanted to have. So the prime responsibility of this fully connected layer is actually to classify. So this fully connected layer helps you, it's a fully connected layer, a classifier, and again classifier will include certain parameters, and then this will help you in finally taking the decision whether to classify a particular image with a normal label or normal label. Right. So now, yes, we have a lot of advantages with this CNN architecture because of this convolution layers. We get basically three different advantages. So CNN basically yield two different advantages. One is we are going to share the weights across the kernel. When we use a particular filter, and the filter will move across the image. So when it moves across the image, the same weight value is going to be applied on every part of the image. So when the filter slides across the image, the same set of weights are going to be used through this scanning of the image. Okay, so that is one advantage that we have with CNN. Besides that, the connections, the connections, the neurons in these representations are not going to be densely connected. Okay. On the other hand, if you could think of what is inside fully connected neural network, so you will have, let's say, after flattening with the final feature map, let's say you get 100 real values, so that you will have 100 neurons in the first layer of the fully connected network, and then you can have, let's say, another 200 neurons, and then you can have another 300 or 400 neurons in the next layer, and then finally you have two neurons, which is going to help you take the classifier decision. Okay, so now in this case, what will happen? So every neuron in the first hidden layer will get connected with all the other neurons in the second hidden layer. And then every neuron in the second hidden layer will get connected with hidden layer. And similarly, all the neurons in the last hidden layer will get connected with all the neurons in the output layer. Okay, so this is how the fully connected neural network is going to be visualized. Okay, but in this case, the number of parameters are going to be very, very high compared to the number of parameters which are involved in the convolutional layers. Okay, because in case of convolutional layers, as we have the notion of filter, and the filter, every filter will not actually get connected with no, every neuron in the next layer. Okay, for example, there is something called sparse connector. Let me assume that I use a 2 cross 2 filter here. So this 2 cross 2 filter will not get, these values will not get, these neurons will not get connected with every other neuron in the next layer. Rather, so it will have only sparse connectivity. So since we have the sparse connectivity, so this sparse connectivity helps us ensure that we have relatively less number of parameters when compared to the number of parameters in the fully connected layers, fully connected layer or fully connected neural network. Okay? So because of these two advantages of CNN, so CNN became very popular, especially in the space of computer vision, and moreover, it is adapted to various domains as well. Okay, so this is some preliminaries about CNN, and now let us understand how transfer learning actually helps us in training the CNN network for a particular domain. So now assume that we have already chosen a particular network from the CNN family, that is BGG16, so which is already trained on ImageNet dataset. It knows how to extract, these neural networks, these architectures basically knows how to extract features from image. Okay, irrespective of the domain from which these images are coming. But anyhow, whatever image is given to these models, it will be able to, in its own style, it will be able to capture the features out of it. Okay, but obviously, when we apply these type of models on medical domain, so we cannot use these models as such, because these models are basically trained on imaginary data sets, which is completely a different image recognition task. Okay, because the natural images are completely different from the medical images. Okay? But when we wanted to actually take advantage of these models, which are already trained on imaginary data set, and we still wanted to adapt it to some other domain, completely a different domain like healthcare or agriculture or any other domain of interest. Okay? So when we wanted to do it, what we basically wanted to do is, so we don't want to alter, we just wanted to keep this feature engineering part or the convolutional layer or the convolutional layer part as fixed. So we want to just fix it as it is, which means whatever features that these models are learning from imaginary data set, and in the same way, let this model also learn features from the medical domain. Okay. And now what we basically do is only to fine tune this fully connected layer alone. Okay. So we would, which means we would only fine tune the classifier part, which means we would keep all the learned by these models on this imaginary dataset as it is, even when we are attempting to adapt it to a medical domain. So we will keep all these parameters fixed, and we would try to fine tune only the parameters of the fully connected layer. And while fine tuning the fully connected layer, which means while fine tuning the parameters of this fully connected neural network, and we would make use of this data set that we have. Okay, so this is where the domain adaptation takes place, and we are now fine tuning this CNN architecture for a completely a different task. Okay, earlier it was trained on recognizing natural images, and now we are fine tuning it such that it is now be able to understand and make a diagnosis decision on a medical domain. Okay, so these two are completely different domains, but still we don't want to, we want to optimize the computations involved in fresh training or complete training. We don't want to do it, okay, because that task may be very expensive, as each of these models involve millions and millions of parameters, and again training a model afresh on this domain specific data set that you have, it is not going to be computationally feasible sometimes. Anyhow, nowadays we have all high-end GPUs available, so that we are able to train model from scratch. But still, no, it is completely efficient just by keeping all the weights in the convolution layers as fixed, and then we try to fine-tune only the fully connected layer. Okay. As I've already mentioned, the number of parameters in the fully connected, number of parameters in fully connected layer is going to be much larger than the number of parameters in the convolutional layers. Okay. But still, we cannot use the classifier parameters as it is, because we wanted to adapt it to a different domain, completely a different domain. So it is a good practice to fine tune this fully connected layer network, fully connected network. But still, we are able to at least to save this part, right? So we are not going to alter these parameters, so that the further fine tuning process is going to be computationally efficient. But still, you are able to actually make use of existing CNN architecture on a completely a new domain, that is medical domain in our case. Okay. So this is the powerful idea in deep learning, where transfer learning actually helps us to transfer knowledge that the model has learned from a particular domain into another domain, which is entirely different from the initial domain. Okay, so here the ImageNet contains a set of natural images, and here our dataset contains set of medical images, which are from two different domains, right? So there is no physical coherence with that we can see, given an image from ImageNet dataset and then given an X-ray image, so which are going to be completely different. But still, we are going to efficiently fine tune the model, so that it can now work well on it, because it is experimentally tested. So transfer learning is a very successful idea in deep learning, especially to fine tune CNN, which are trained on different domain, and then we wanted to fine tune it to another domain, fine tune it to a domain which is completely different from the source domain. Okay. So it is this is what called transfer learning, as you could understand from this figure. So there is a source task. Probably you can think of these models which are trained on ImageNet. And now you pick up one of the models from a source domain. I just pick up VGG16 in this case, and then I'm going to keep the convolutional layer or the feature engineering part of this VGG16 as it is, without altering it. Whatever weights that this model VGG16 has learned from ImageNet dataset, I'm going to keep it as it is. So I'm going to keep it as it is, and then I'm just going to fine tune only the parameters involved in the classifier. Okay. And while modifying or while updating the parameters of the classifier, I will make use of this data set, a domain specific data set that you have at hand, so that now the classifier parameters are learned according to this particular data set, a new data set. Okay. So that is where actually the knowledge, no, the knowledge transfer happens, basically from the source domain to this target domain. So here the target domain is medical, and the source domain is set of natural images. And now we transfer some knowledge that these models have learned from ImageNet as it is to the target domain. And besides that standard feature representation of feature knowledge, so we are going to add some domain specific knowledge as well to the classifier network, so that now our model will be capable enough to work on a completely a different data set, a completely a different domain. Okay. So this is the idea of transfer learning, and let's move on, and then let's look into further details. So basically, you can look at, consider this architecture, a simplified architecture, as VGG16 architecture or any of the CNN family of architecture. Okay, so which is basically configured in order to find the mapping from X to Y. So while X could be an image, a medical image in general, and then Y could be an output label. In case of a binary classification problem, it is going to be 0 or 1 infected or not infected, or diagnosed with abnormality, or diagnosed with no abnormality, and so on and so forth. There is a presence of cancer tumor. There is no presence of cancer tumor. The patient is diagnosed with a particular health condition, and a person is not diagnosed with no notable medical significance. Okay? So you can think of output label as anything, and you may be even interested in assigning more than two labels as well. So appropriately, the problem that you have at hand, a classification problem that you have at hand is different. So it could be a three-class classification problem, or it could be a five-class classification problem. So given set of cancer medical images, okay, medical images obtained from different cancer patients, and now you wanted to basically assign labels to each of those images that has presence of cancer tumor. Okay, based on the severity of the cancer. So whether the patient is in stage 1 or stage 2 or stage 3 or stage 4 or stage 5, and so on and so forth. Okay. So appropriately, you will be basically dealing with different classification problem. Okay. So I have not taken the original BGG16 architecture as it is. I have taken an example of some neural network, a random neural network, and I just call it BGG16 so that you get an idea that BGG16 is a CNN architecture, so that it will have two parts. So one part in which feature engineering is performed, which will help us to learn no significant features or low-level features from the training data that we have, and then we will have the final fully connected neural network or fully connected layers, which is responsible for taking the classification decision. And now what we are going to do is so we will just keep the convolutional layers as it is fixed, and then we will try to fine tune the fully connected layers. So now, yeah, considering this standard architecture, so initially the model has been trained on, let's say, image recognition task from a natural domain, okay, natural images. And now we wanted to fine tune this model so that it can now work on radiology diagnosis. Okay, it is now going to make model is now going to make radiology decision or healthcare decisions based on medical imaging. Okay. So now we wanted to transfer the knowledge that this model has already learned on the set of natural images to this domain so that it can use the same set of features that the model has learned from no natural images, and same completely different domain. So in order to do it, what we basically do is to probably in case you have the fully connected layers here, and those fully connected layers will now be fine tuned according to the dataset that you have from the radiology domain, and then we would appropriately fine tune the model. Okay? So when we fine tune model using transfer learning, the biggest advantage that we get is this learning, training, applying transfer learning for learning a neural network or learning a convolutional neural network for a particular domain, so will be computationally less expensive, because we are not basically training the network from scratch on the new data set, and we are going to basically freeze all the parameters that the model has learned in the convolutional stage. Okay, so we are going to alter only the parameters of the fully connected layers, so that now the model with less of computational efforts, we are able to fine tune it for a completely different domain. So that is the biggest advantage that we get from the transfer learning. So transfer learning has proven to be very successful in the recent days. There are thousands of papers on transfer learning, which has which has been found suitable in many domains. A lot of implementations being tested on medical domain, agriculture domain, and then whatnot. Ah, right. So again, when it comes to weights, when it comes to parameters of a model, so there are different ways you can choose initial set of parameters. So again, choice of initial set of parameters is very important, no, especially to ensure faster convergence of convolutional neural network, any neural network in general. Yeah, because you can sometimes make a random choice of values for weights and biases, so which are part of the neural network. Okay, you know that every neuron in the neural network will be associated to a set of weights and biases. Every neuron will be connected with some bias, and similarly, when neurons from one layer gets connected with neurons in the other layer, then each of these connections corresponds to a weight. Okay, similarly, this will also be connected with every other neurons in the next layer and so on. Right? So this, but anyhow, while learning the features from the while learning features from the image, so we are going to use convolutional layers, and convolutional layers have certain advantages. Okay, which helps us in weight sharing, as well as we are going to have sparse connectivity, so that finally it yields us less number of parameters compared to the number of parameters that comes from the fully connected layers. Right. So besides that, yes, anyhow, we are going to freeze all the convolution layers, and we are going to only fine tune the parameters from the fully connected layer. Okay. So now, yes, as I mentioned before, the initial choice of weights and biases are also equally important. Okay, because it can help us. It can help model that it converges fastly. Okay, you don't want to run several thousand epochs, before converging the model, before witnessing that the model convergence is positively happening. So we wanted to probably run a few hundreds of images or few tens of few hundreds of epochs of. So if your data is extremely complex, then in order to understand the mapping from X to Y, model may consume a lot of epochs. Okay, in case your data is simpler, or data has not much of complexity, like if your data is in the form of, let's say, tabular column. Okay, as standard machine learning algorithms expect the data representation to be. Okay. So in case you wanted to work with such a structured CSV kind of data using some deep neural network architecture, then your data is going to be simple, right? When it is already structured and it is not complex, as compared to the image or signal or voice kind of inputs. Right. So on the other hand, yes, model can also be simple as well as complex. Most of the architectures, most of the models that we see in deep learning families, those are very complex because model takes a lot of parameters. Okay. So you can simply accounts to the number of parameters so as to define the complexity of a model. If the number of parameters are high, then the model is complex. Okay, if the number of parameters are less, then we can say that the model is relatively less complex. Okay, so that is the way how we make it. So especially now, again, there is a trade-off here. So there is a trade-off here. Uh, Data could be a trade-off between data and model is important, and that's where the ML engineer or deep learning engineer they would help you. Okay, so in making a right model for the data that you have at hand, or the data that defines a particular task that you have at hand. So if the data is simple, then it is good to go with a simple model, and if the data are complex, then we supposed to have adequately a complex model so that it can understand a complex pattern that is inherently present in the training data that you have. Okay, so in case if you try the other way around, let's say your data is simple and you're trying to, let's say, learn a complex model. Okay, so in this case, probably the convergence would be faster. In case you observe that the convergence is happening very faster, then you can understand that the model is relatively complex, but data is simple. So this complex model is able to understand the mapping from X to Y from as the data has no much of complexity. So model is able to learn very well from the data set. Okay. And on the other hand, if you are trying to learn a very simple model for a complex data collection, then this model would never converge because the model will be keep on making a lot of errors, and thus you will be moving on to different epoch. But but at none of the steps, at any step, in the learning process, so we'll be able to find out right set of parameters because the model that we are playing around is very simple, but and which is not capable to understand the inherent complexity of the data that you have at hand. Okay. Yes. Again, there is a good trade-off that you need to follow here, and that is where a lot of experimentations are required, and experimentation will help you, decide what is the right model. And, the choice of model. You can basically take a wise decision on the choice of model so that you can appropriately take it for fine tuning. Right. So these are something that I've already explained. Yes. Uh, I'm going to afresh learn the fully connected neural network with the help of radiology images I have. Okay. So these parameters, I may have fully connected neural network here as well, right, but which are tuned based on the source data. And now I don't want to use that any longer because this source task in which I may have, let's say, 10 classes or 15 classes or 20 classes or even 100 or 1,000 classes, but in the data set or in the domain that I'm currently working on has, let's say, only two classes. So I cannot use this fully connected neural network as it is, and I need to customize it. Okay? So now I introduce my own fully connected neural network with a number of neurons which are adequately required for taking this particular classification decision. Okay, so it is a basically a binary classification problem. So I can either have one neuron at the output layer, or I can have two neurons in the output layer. Okay, so in case if you have one neuron in the output layer, so you can have a threshold appropriately. So if this neuron actually fires a value above 0.5, you can map it to, let's say, class 1. And if it fires value, let's say, greater than 0.5, then let the label be 1. And if it is less than 0.5, then let the label be 0. Okay? So this is the way how a single neuron output layer behave when it comes to solving two class classification problem. So on the other hand, you can also have two neurons in the output layer so that the output fired by the neurons in the output layer will then be represented in terms of probability distribution. Okay. So that when you count the values of the output layer, when you sum them to, it will be equal to 1 because it will be represented. That's where the all that comes in. So that will help you convert real value figures into probability distribution, so that you can appropriately use a relevant loss function in order to estimate the performance of the model. Okay, the model is making error which is far beyond. If the model is making huge error, then again you can go back and then fine tune so that you can alter the parameters appropriately so as to arrive at the final set of right parameters. Yes. So now we are going to expose this new data to this fully connected neural network so as to understand, so as to fine tune the parameters. Primarily called yes, transfer learning actually gives us promising results, in most of the computer vision tasks. But when does it actually make sense? Yeah. So what actually drive us to go towards transfer learning? Should we blindly choose transfer learning, or is there any relevant conditions so that you appropriately go with transfer learning? Yes, there is an option. There is an option, and it is very straightforward. Let's say if you have huge amount of huge number of training instances as part of your data. So the data that you have at hand for building a classifier for a particular domain, for which you have adequate number of training samples. Let's say for predicting a medical diagnosis. So we wanted to find out whether the person is infected with a particular medical condition or not. Okay, in order to make a binary classification decision here. And now let us assume that the training instances you have is extremely large. It's like you have 10,000 plus samples for defining normal conditions, and then you have 10,000 plus images for abnormal conditions. Okay, I think 10,000 is fairly a good number, especially to construct a two-class classification, two-class, especially to solve two-class classification problem. So for two-class classifier, I think if you have, let's say, 20,000 images, training instances as part of your data, and that is adequately okay. So in order to learn the classifier right from scratch. So in that case, if you have adequate number of samples in your training set, so you need not actually prefer to go towards transfer learning. Okay, so as I've emphasized before once, transfer learning helps us to converge the model with less computational efforts. And that is primarily one of the advantages of transfer learning. So besides that, nowadays, considering the amount of computational resources we have, we even have GPU access in every desktop. So which means even desktop computers can also be used to some extent in order to train relatively complex models. Okay, right. So when we try to do that, when we are even able to fine tune even large language models. No, I'm not talking about a large language model of a very complex model like GPT sort of thing. I just mentioned that for small language models we have, a lightweight LLMs we have, open LLMs which are lightweight, which has no more than let's say 1 billion parameters. So we are still able to systematically train with the help of very limited GPU that we have locally in our desktop. We are able to fine tune even such large models. So in that respect, model is very important than the computational requirements. Okay, we cannot compromise the model just to save the computational efforts. Okay, so in case our focus is to build, because we are now trying to build a model for medical domain, which is very sensitive. We cannot compromise, right? Even if it requires enormous computation, so we should be able to, we should be able to carry out the enough of computations so as to build a proper model. Okay, we don't want to basically save computation, or we don't want a faster convergence, because the domain is very sensitive. Yes, of course, these two have advantages. We need to get these advantages. Besides this, the performance of the model is much more important compared to the number of parameters that the model has, or the time taken for us to train the model. Okay. In that case, basically the choice we make whether to use transfer learning or not, it basically depends on the amount of data that you have at hand. So in case the domain specific data that you have is reasonably large, then you need not go with the transfer learning, and you can relearn the model right from scratch on the new dataset that you have, a domain specific dataset that you have. Okay, so that is how actually we see whether the transfer learning will make sense okay, in the application that we are working on. In case the domain specific data that you have has no large number of samples. So the number of samples that you have in your domain specific data are very, very less. You have probably, let's say, 100 images of images of normal condition, and then another 100 images of abnormal condition. So in that case, the 100 is relatively a very small number, right? So you cannot use the 200 samples to learn the model completely from scratch. Model will not learn much from these 200 images because model is extremely complex. And what can complex model learn from simple data, which has no less number of samples? Okay. So this setting is not appropriate. And in this case, we decide to go with the transfer learning. So let the model preserve whatever features that the model has learned from the source data set. Let the model preserve all of them as it is. And let us now try to infuse the possible things that model can learn from this domain specific data set, which is relatively small in size. Okay, so this is the right setting where you can decide to use transfer learning. Okay, so if you have, as we have assumed earlier, if you have, let's say, several thousand images like this, you have 10,000 K images of normal, 10,000 sorry, 10,000 images of normal condition, 10,000 images of abnormal condition. 10,000 is fairly a big number. So in this case, you can afford to completely train any of these CNN model from scratch. Okay, but in case if your new data set that you have has very less number of training samples, and this is the right use case where transfer learning can help you train a fairly reasonable model that can be used on a domain specific setting like agriculture or healthcare or any other domain of interest. Yes, we see the difference between two terms that we predominantly use in the context of training deep neural network. So one is pre-training, the other one is fine-tuning. So pre-training in the sense the model that has already learned from some source data set, right? So the weight values or the parameters that the model has learned from the source data set. So they are called pre-trained weights. So these weights are basically learned from the source task. And now we wanted to fine tune, which means we wanted to relearn only those weights which are part of the classifier module, which means the fully connected neural network. Okay, we wanted to fine tune only the weights of the fully connected neural network, and for which we use the term called fine tune, which means we are discarding the pre-trained weights of fully connected neural network, and we want to learn it afresh with the help of the new data set that you have. Right? So this is the difference between pre-training and then fine-tuning. So basically for fine-tuning, we would make use of the domain-specific data set that you have, and the pre-trained weights generally are learned from the original data set on which the model has been trained. Okay. So now the knowledge that the model has learned from the original data are actually passed on to is going to be used. The knowledge that the model has gained from the original data set that is part of a different application is now going to be used by this new domain. Okay? Besides being fine-tuned with domain-specific images or domain-specific data. Yeah. So here is the question. So why should transfer learning work? Okay. So basically, the learning low-level features such as lines of simply pixel whiles features, edge features, curves, possible other object structures from any image. These could be a valued set of features even in other domains. Even a line feature, dot feature, edge feature, curve feature. No, these could also make sense from the medical domain as well. So that is the reason why these low-level features can be kept intact, and let us also let the model in the domain-specific task also learn the same set of features. So that is the reason why we are just freezing all the parameters of the convolutional layers, so that your model will still try to learn or identify line feature, line dot edge, curve, and other object structural features from the medical domain or the domain specific data set as well. Okay. So only we are going to fine tune the classifier, so that the classification decision is going to be taken not based on the source domain but on the destination domain or the target domain, the domain specific data for which we wanted to build the classifier. So in this setting, transfer learning can work, and then, as I mentioned before, there are a lot of people who have taken advantage of this transfer learning, and they have transferred the knowledge that the model has gained from the source data to a completely a different domain, and model has been found to be working very fine on the completely a new domain for which you have less number of data samples. Okay, as expressed in this slide. See, the original model has actually been trained on a data set which has millions of samples. Okay? So it has enough of samples so that the model could be freshly trained. Now, when it comes to a domain-specific task, you have a problem from the medical domain you have. So let's say you have only few hundreds of samples, right? So these few hundreds of samples are not adequate for training a large, complex deep learning networks, right? Or deep neural networks or any deep models, right? Because the deep models or even machine learning or deep learning or deep models are basically data hungry models, so which requires enormous data samples in order to train a model afresh. Okay, if you have a few tens of few hundreds of images, so that may not be adequate to freshly train a model, because models are extremely complex, and you must have a reasonable complexity that the model can capture from your data itself. So if you have only few samples in your data, and that may not be sufficient to train a complex model, right? And moreover, in this case, we cannot bring down the complexity of your model. If you bring down the complexity in order to adjust with the number of samples you have, so you are actually making a mistake. Okay? Because once the system is deployed, and unseen data are going to come to your model. Okay, your model should now be able to approximate the knowledge that it has learned from the known data to an unknown data, right? So you cannot basically compromise the model complexity just because the number of samples that you have in your data set is less. Okay, so that way of addressing this problem may not be fair. Okay, so even if you have hundreds of samples from a medical domain, and these data sets are also equally complex because they are like X-ray images, which are basically used for sensitive medical diagnosis outcome, right? So when compared to the complexity of standard natural images you have, the complexity of medical images are extremely high, especially if you consider other images like MRI, CT scan. Basically, the machine captures images of a particular organ from multiple dimension, multiple orientation, and then finally it is going to stitch all these images together, and final outcome is going to be in a final image is going to be a two-dimensional, a single two-dimensional image. Right, it's going to be just one image which is represented in two-dimensional space, but basically the images are actually captured by multiple cameras, and then a new image is synthesized out of this image. So you can imagine now that complexity of such an image that comes from the medical domain. So you cannot, just because you have less number of samples, you cannot say that your data is simple. Okay, I didn't mean that. Because your data is in the form of images, maybe in terms of resolution, maybe represented at high scale, so that data are more complex when compared to the data set of your source task. Okay, so you cannot basically alter the complexity of the model. That's why we still wanted to preserve the complexity of the model, because model should be capable enough to work on unseen data, most importantly. Okay, it is not just about training a model and then we report results of the model on some portion of the training set. So we want the final model to work well on work well on unseen data. So that is our target. Okay? That is the reason why we go with transfer learning without minimizing or without adjusting the complexity of the model. Um, yeah, this is something that we have already discussed. Right. So basically, we wanted to transfer knowledge from task A to task B, and task A is done on, let's say, a set of natural images, and there is a model which is trained on natural images and for a particular image recognition task. And now you wanted to take it to medical domain. That is task B. Well, now you are going to make use of the same model. And now what we wanted to do here is, so whatever the low level features that model has learned from this set of natural images, let us try to transfer them as it is to another domain of interest that we are working on. So besides that, we are going to still fine tune because naturally it will not work. Maybe a randomly sometimes, sometimes VGG may work very well on completely a different domain. Maybe because of its better generalization ability, model can perform well even without fine tuning. Model can, as it is, whatever the model that is trained on the primary data source, and if you just deploy it as it is on completely a new domain, maybe to your luck, sometimes it may work well, but practically that may not be always possible, and fine tuning would be required. Okay, so while doing the fine tuning through transfer learning, and you are able to ensure that the low level features that the model has learned from the original task are going to be preserved even for these domain specific tasks. And that is the biggest advantage that we get out of transfer learning. Yeah, this is something that I've already shown. I have a good picture here. Yes, so here is the feature engineering part. Feature engineering part, CNN layers, so which are going to be kept intact. And then we are just going to, oh no, it's up to you. You can even see here as shown in this figure. So you are even discarding some of the CNN layers from the architecture, and you add your own set of layers here. Okay? It is up to you. So which means, yes, you keep the layers of dense layers as it is, but additionally you are discarding. Okay? So these are some of the experimental choices that you make. Okay, no one can basically guide you, and depends on data that you are operating on, depends on the domain on which you are working on. You can make these wise decisions, maybe based on your expertise with training, fine tuning deep models. You can take these decisions, and no one can say no wrong or right about it. It all depends on the experiment. When you conduct, maybe you can take it as one of the use cases in experimentation, and then you can consider this as one of the experimental setting, and then you derive some results. And if it is satisfactory, then you can go ahead. Or if it is not satisfactory, probably you can once again retain this layer, and then you can check whether the model is working better than the previously fine-tuned model or not. Yeah. Right. Yeah. So in one go, we will not be able to decide our model, and many more experimental settings that we may have to actually examine, okay, so that we finally come up with the right model for the domain specific data. Right. Yes. So the reason why we need to alter a fully connected layer, which means most importantly, yes, the primary the data set of the primary task of the original task might be multi-class classification problem, but the domain-specific task that you have has less number of classes to handle. So that is the reason why we prefer to basically fine tune this fully connected layer. But all the low level features that the model has already learned will be kept as it is. Besides that, a new set of domain specific features will be learned from a small scale domain specific data that you have. We don't ignore that. We keep the low level features that the model has learned from the primary data. Besides that, we also enable model to learn set of features from the small scale data set that you have from a domain specific task. Okay. So thereby we actually enhance the capability of the model now, so that we are able to adapt the model trained on the different task to a specific task that you wanted to carry out. Yes. So now, yes, that's all about transfer learning. Next, we'll move on to something called multitask learning. As I mentioned before, multitask learning is something that is proposed in 1987. So it's a very old framework. When compared to transfer learning, multitask learning is not so popular. It is not widely regarded. It was popular once upon a time, due to the benefits we derive from transfer learning, multitask learning is not so widely regarded and not so often used in the current scenario. Okay. In the current trend, we still go behind transfer learning compared to multitask learning. But multitask learning also makes sense in some interesting use cases in computer vision. Let me take you to one such use cases. One of the use cases where we find interesting insights that comes from multitask learning will be more suitable. Right. So Ashwin, that we are trying to build an autonomous driving sort of driverless cars, where driverless cars are basically a computer vision based model, because which has the capability to learn the possible hindrances that the vehicle can observe when it is in mobility, right? So the device, the driverless car should be capable, so as to recognize the pedestrians, at least identify, not identification, at least it should be able to detect. Right? So there is a difference between identification and detection, right? So detection is all about there is a pedestrian, right? So identification, who the pedestrian is. So basically, the driverless cars do not need that ability, but at least it should be able to uh, it should be able to identify that there is a presence of pedestrian, so that the vehicle is supposed to slow down or it's supposed to stop. If there is any stop signal, it's supposed to stop. If there's a traffic lights, and accordingly, the car is supposed to take decision, so that to move on or to stay back and so on and so forth. Yeah. Right. So now, in such a case, the model is expected to actually detect objects of different kind, not just one object alone. Okay, as we have seen in the previous use case, where we wanted to make decision on health condition, right? So the decision is only two. So whether the image is of a normal patient, or an image has some sort of abnormality in it. And this is the only two decisions we wanted to make. But this task is going to be a bit complicated compared to that domain specific task. So here we wanted to actually detect objects of different kinds. So the driverless car is expected to detect pedestrian, car, stop signs, traffic lights, and so on and so forth. Okay, why just car alone? It should even detect vehicles, two-wheeler, motor vehicles, cycles, and whatnot. Everything should be detected, right? Because it cannot ignore anything. So it should even be able to detect trees, or any other form of obstacle that the driverless car can experience on road. Detect car and should be able to detect stop signs, traffic lights, and so on and so forth. Okay, so basically we wanted to enable model to learn or identify or detect multiple objects from the image. Okay, so the one simple solution to this problem is that you may train an individual neural network for each of these objects. So you can train a neural network for detecting pedestrians. You can train another neural network, completely another neural network for detecting car, and completely another neural network for detecting stop signs and so on. So this is one simple solution, but is it really needed? So should we really train independent, a neural network, so as to detect objects of different kinds? It is basically not required because there could be some features which could be common across various object categories. For example, features, especially when it comes to low-level features, as I mentioned before, there could be features of lines, features of corners, features of pixels, of a kind of dot, or sort of any shape sort of features. Low-level features could be same in each of these object types, right? Some features that might be commonly used in detecting pedestrian as well as car. Some features might be seen in common in both car object as well as stop sign objects, and so on, right? So there are possibilities, right? So why don't we miss out? So why don't we just train a single neural network that is able to detect objects of multiple kinds so that a common features could be utilized. Okay, it's a kind of save, right, in terms of computations, right? If there are, but we do not know what are those features which are commonly seen across object categories. But anyhow, if we could combine learning or detecting objects of different kind using a single neural network, and the network will be able to inherently utilize common features. So even though at high level, when it comes to objects, and these objects are completely different from each other, but when we look at the low level features, yes, of course, there could be some common features. So that is what all that I mentioned, right? Because of course, it seems like no, we wanted to make a decision on multiple objects so that it looks like the architecture looks like a multi-class classification problem. That's where this softmax activation helps us, to represent the outcome in terms of probability distribution. Yes, of course. Yes, we have the mentioning here of loss function, as we know, is while we train the model, and once we learn initial set of parameters, then we would assess the loss of the model. Okay, so how much error that the model is making. So based on the amount of error that the model is making, so we would go back and then we would tweak the parameters of this model, and then we would take the decision on the training set once again. And if the loss is actually expected to reduce over time, so over and no, over and over different epoch, and the model is expected to actually minimize the loss. Okay, that is what we basically plot loss curve, and then we see that there is a linear reduction in the loss. Right? But sometimes it may not be possible if data are extremely complex. Sometimes you would experience some sort of spike in the learning curve, right? Even though there is a convergence, probably the convergence would take more time, and on the go, there will be a lot of spikes observed. Okay, so again, you can play around hyperparameters of the neural network family that you are training, and you can just play around with it, and then you can appropriately even smooth the loss curve as well. Yeah, this is something that we have seen, but this solution is not promising because no need to basically train four separate neural network, one for each of the object categories. And in this case, if we are able to, if we could train a single neural network, so that the single neural network would make use of common features at low level of different objects, so that we would see improved performance, especially when we train a multitask learning model. Okay. So here the loss function, let me quickly, it is a simple loss function. We just compare the predicted label with the original label, because the classification task is basically a supervised learning task. So we would have the known label as well as the predicted label, and then we just compare it, and we can use appropriate loss function here. Actual loss function is not mentioned here. So only the mathematical representation of the loss is mentioned here. So we just compare these two. For comparison, you can use any of those available loss functions you have. Right. Most importantly, predominantly we see this cross entropy loss. Yes, you can use cross entropy loss here in order to compare two two probability distribution. Okay. Right, and then yes, we have four different object categories, and M is the number of training samples you have. So we just approximate this loss across the number of training instances you have. So M could be the number of training instances, or you can probably have it have a batch size of M, so that you can need not actually check the loss across the entire training set, and you can probably assess the loss on a particular batch size. Okay. And then you can go back and then tweak the parameters, and then you can ensure that the loss is getting reduced over epoch. Yeah. So this is very important. So meantime, if there are any questions, I don't have access to chat window. If there are any questions, probably you can let me know. Yeah, there is a chat window here, but in case you have any questions, you may please type in the chat window. Okay, fine. So here is the right setting. So when should we use multitask learning? So this is something addressed in this slide. Right. Yes. So one advantage of multitask learning is to is to share the low-level features. Okay. Sometimes the objects of different kind may have common low-level features, so which could be utilized by the model. So this is one advantage. So besides that, assume that okay, so you have uh, samples. And for detecting pedestrians, you have only 1,000 samples. And for detecting traffic lights, you have 1,000 samples. And then for detecting stop notations, you have, let's say, 1,000 images, and so on. Okay. Then for cycle, you have another 1,000 images. For detecting, let's say, um, uh, motor vehicle, you have 1,000 images, and for detecting trucks you have 1,000 images, and so on, right? So now basically we wanted to train a single neural network for hundreds of these tasks. Okay, so tasks of this kind, basically there are tasks from T1 to T100. Okay, so now we wanted to learn a single network, train a single network that is able to recognize 100 different types of objects at the same time, right? So now if you just focus on one of the tasks, one out of 100 tasks that you have at hand, so what can happen in this case? Say now for this particular task you have only 1,000 samples, so you have only 1,000 samples. 1,000 samples are so fairly a good number, right? So 1,000 samples are relatively a small number, and even for training a network for a particular task with just 1,000 samples may not be adequate, right? Right? Because 1,000 samples which are of image, uh, which is not actually considered okay. We must have at least 10,000 or 20,000, 30,000 images so as to train a meaningful image classification model, right? So in case if we have data instances in the form of tabular representation, I think 1,000 instances would make sense. Probably the 1,000 samples would cover all possible combinations of various columns or attributes that you have in your data set. But the 1,000 images of a particular object kind may not represent all possible representation of that particular object, right? So that is the reason why I say that the 1,000 samples are not a good number to have for training a model. that task. So what we can advantageously do in this case. So while learning, while learning or while tuning this model for, let's say, a particular task, with 1,000 samples. So now there are other remaining 99 tasks which are also being parallelly learned, right? So what this one task can do, it can take advantage from all the other low-level features that the model has learned from the remaining tasks. So that is one extra other advantage that this multitask learning actually gets, right? Say for example, yes. So especially when we have less number of samples for each of the object categories, so it is we are actually inherently getting advantage from the other tasks which are being learned. Okay, so task one can take advantage from, let's say, task 2 to task 100, and task 2 can take advantage from task 1, and then task 3 to task 100, and so on. Okay, the remaining 99 tasks, the low level features of the remaining 99 tasks can be used by this particular task, so that this 1,000 samples are no longer inadequate number of samples, because considering the total number of samples that you have across tasks, so you can definitely be able to build a much better multitask learner, which is able to actually solve all the 100 tasks at the same time. Okay, so that is the takeaway here. But on the other hand, while comparing transfer learning with MTL, so if you have 1 million samples, let's say, for a task A, and task B has, there is some commonality here between transfer learning and multitask learning. Multitask learning in very similar to the way how transfer learning works. Okay, because use transfer learning because the task A has been trained on very big uh, collection of training instances, but now the domain specific task B that you have at hand, which has less number of samples to use for training. So now here you are trying to augment the features that the model has learned from the that both transfer learning and multitask learning appears to be very similar to each other. Okay? But on the other hand, okay, so what is the caveat in multitask learning? The limitation of multitask learning is that, right? Yes, of course, you can either run a single model for all the tasks together, or you can train individual neural network in isolation for different tasks. Okay, so in case so only times that multitask learning hurts performance when you have neural network which is not big enough. Okay, which means the data that you have for training neural network is not uh, big enough. Okay, if it is not big enough, then only actually the multitask learning actually suffers. Okay, but you can train a big enough neural network, then MTL certainly should not hurt performance, and it should be able to work well. Okay, so because these models are basically data hungry models, and no data hungry model, and it requires a lot of data. So only this can hurt multitask learning, where you have not adequate, when you have not sufficient data instances of training instances for training the model. Okay. But certainly this setting, the MTL setting, will certainly outperform training individual neural network in isolation on different tasks. Okay, so certainly MTL has good advantage, but when it is compared against transfer learning, yes, in practice, MTL is less often used compared to transfer learning. Transfer learning is predominantly used in the current setting, right? However, MTL has the capability to detect objects, multiple objects at the same time. And moreover, as we have seen, another advantage of MTL that when it is actually learning for a particular task, a particular object, recognizing a particular object or detecting a particular object, and it can actually take uh, uh, advantage from the low-level features that the model has already learned from the rest of the tasks. So that is one other good advantage of MTL, and that also brings MTL close to transfer learning, right? Basically, transfer learning is also of same kind. In that way, actually, MTL actually converges with transfer learning, which means MTL appears to be similar to transfer learning. And so when to use transfer learning and when to use multitask learning. So multitask learning is when your objective is to detect multiple objects, or when you wanted to actually train a single neural network for addressing multiple tasks. Yes, you can go with multitask learning. When it but to solve a particular machine learning problem that you have at hand, so how can we make choice with respect to the amount of data that you have? So if you have relatively small amount of data, transfer learning helps you with no doubt, because you are going to make use of pre-trained model. So pre-trained model has already learned various features from the original data set. And now with the less amount of data instances you have, you try to enable the model through fine tuning so that it can also understand some significant features from the domain specific data set. Okay. Right. So, and then finally, we have something called end-to-end learning. So end-to-end deep learning or end-to-end learning is not always the solution. It is a solution for certain use cases, and it cannot be a solution in many other use cases. Okay? I have some use cases where end-to-end learning will help you, and use cases where end-to-end learning will not help you. Okay, so nowadays most of the deep learning, the problems that we solve through deep learning, so we are basically considering it as end-to-end problem, and we don't actually realize that some intermediate steps are also required. Okay. So let us consider this speech recognition case here. So given an audio clip, and we wanted to get its equivalent transcript of that audio clip. Okay. For example, nowadays even NPTEL videos comes along with a transcript, right? Even if you watch any course in Coursera, you can also access the transcript of a particular video lecture. Okay, it is all available. Both of them are physically available, and we can do it. It is not manually done, so manually doing this task is not fair and may be accurate, but it will be time consuming. But we wanted to do it. People attempted to do it automatically. So this when no manually done traditionally, this is how this approach, this solution was designed. So given an audio clip, so they use some pre-processing algorithms so as to extract features from audio clip. The audio is basically a kind of signal, right? So they extract some kind of signal features from audio clip, and then people have used some ML algorithms in order to extract phonemes from features. Okay, so from the signals, so they can extract phonemes. Okay, phonemes means a kind of sound. So every word can have multiple phonemes. For example, there is an example given here. There is a word cat, and cat has three phonemes. So ka, k, and a, and then t. Okay, so these phonemes together, when it is stitched together, it becomes a word. So we extract phonemes from features, and then by stitching phonemes together, we get words, and then by stitching words together, we get the final transcript of the given audio sequence. This is how earlier this problem was addressed, but now we have sophisticated deep models, so which can consider this task as an end-to-end learning task without focusing on intermediary steps like feature extraction, phoneme extraction, word extraction, and then probably sentence construction. Instead of doing it in multiple steps, we just decided to do it in a single step, right? Because we have extremely complex models which can straight away find the association between X and Y. So that is something that is attempted, and it is found to be relatively better compared to doing it in a traditionally non end-to-end fashion, right? Okay, so these experiments have been tested at high scale experiments as well. Okay, but as these end-to-end deep learning frameworks are data hungry, again you can make a trade-off here. You can make a choice here. So when to use traditional? At the same time, we cannot say that the traditional systems are bad. We cannot say that. So if you have less amount of data to train such a model, which can help you, translate, or which you help you convert from audio clip to its equivalent transcript form. So if you have less amount of data, then your traditional system still works better, okay, compared to deep models. But if you have relatively large collection of data, then these end-to-end learning frameworks would definitely yield better results compared to non-traditional, traditional way of doing it. Well, this is one use case where end-to-end learning actually gives us an advantage, but at the same time, it depends on the amount of data that you have. So if you have less amount of data, like you have only 3,000 hours of audio data to train such a model, because 3,000 hours of data not so relatively large in size, so you can better go with a traditional non-end-to-end way of doing it. And if you have, let's say, 10,000 hours of audio file, so as to do this, so as to find this mapping, probably 10,000 hours of audio file would mostly include all possible distributions which could possibly be captured by the model, and then so that it can flawlessly construct the transcript for the given audio file. So on the other hand, when it comes to face recognition, right? So we wanted to recognize face. So here comes the difference between detection and recognition. So as you could see here, so detecting is just detecting the area where the face part is appearing in the picture, right? So recognition in the sense, so we wanted to identify the person. So who is in the picture? So there are many applications, applications in probably security systems where face detection is not of much importance, but face recognition is of much importance, right? So especially in an organization setting, right? You wanted to allow only those people who are authorized to enter into the campus can be allowed, right? Like it's not. It is about basically detecting a face as well as recognizing the face. Fine. Right. So now, in such an application, right, and you might have seen this type of desk in airport or in railway stations, right? So as once your face is recognized, and if you are a valid passenger, so only then this door opens, and then it will let you go inside, and then do the rest of the travel formalities. Okay. Yes. So in a naive approach, you can think of considering it as an end-to-end deep learning work, and you can directly find association between X and Y directly. Or on the other hand, you can do it in multiple steps. Okay. Especially in this case, it is better to go in multiple steps rather than treating it as an end-to-end work. Okay. So in case if you do it in multiple steps, the first step, try to detect the faces, and then extract and just crop that portion of image from the just crop that portion of the image from the original image, and then you just compare it with your data set, and then find out whether the uh, person can be identified based on the records you have in your database. Right. So it could be done in two ways. One is the detection phase, to find out where exactly the face appears. Especially when you implement a face recognition application in this type of use case, especially in sort of gate entry. So in this case, actually, no, you cannot always expect user to stand at a particular place. Yes, of course, you can do it, but the users sometimes will show only one side of the face, and then some users may come very close to the camera. Some may stand far off from the camera. Right? All these things are also possible, right? So all of them should be dealt. So that is the reason why it is better to first detect the face. Don't just operate on the entire image. Just detect the face, and then you need not do the database kind of match. You need not do one-to-one sort of match, and you can even learn a network for comparing two images. There is a popular network called Siamese network, which you can train, which is again a CNN-based network, CNN-based architecture. So which can help you compare two images, whether they are close to each other or they are from same person or from different persons. Okay, so especially in this setting, it is expected to give an adverse output saying that these two pictures are completely different. Okay, in case if two persons of different orientations are given to this network, and network has capability to identify that both the pictures, which are captured at different orientation, but it is of the same person. Okay. Right. So in this case, basically a multi-stage approach is found to be good, and it is also experimentally tested that multi-stage approach actually works better compared to treating this problem as an end-to-end problem solving. Okay. So here, as we divided the entire pipeline into two parts, yes, now we get a sub-problem, and each of these problems are simple and then well-defined. So the first task is a regression problem. So where you get the coordinate of the presence of phase, right? So you would get this x1 y1 coordinate, and then x2 y2 coordinate. Okay, so this way, or you would get width and height. So given this first coordinate x and y1, and then width and height, so either this or this. Anyhow, you need to extract four real values for each phase. Okay. You can train a regression model for detecting phase, and then you can use this sort of Siamese network for comparing the facial image, okay, to identify the person. And then moreover, we have a lot of data available for each of these tasks, but we don't have much of data available for this direct end-to-end mapping. Okay? Directly identifying a person from any random image, we don't have a huge amount of data. But especially when it comes to just detecting a face, yes, we have large amount of data publicly available. And again, when it comes to identifying a person, yes, we do have large amount of data sets, data available, so that we'll be able to address this problem in a multi-stage manner, not in terms of end-to-end manner, so that we will be able to solve this with a reasonable accuracy. There are other use cases. For now, I may just skip this. And if you have any questions, and you may ask me.